And the process, there's a process and field. The difference between a Gaussian process and a Gaussian field is that the Gaussian process is indexed by a scalar, and the Gaussian field, which is the case of vertical tech, is indexed by a vector. But they are more or less the same thing. So here we have the set of the space of possible functions. If we are able to order them by smoothness, if you are able to order them by smoothness and singularity, you could say, okay, I introduce this idea to some that we will have some of the prior. I mean, I can say, okay, I like more smooth functions than non-smooth functions, but perhaps I want to allow that non-smooth functions might appear. So we could have F1, F2, and for instance, F3. So in this case, we would like that P of F1 is bigger than P of F2, and this is bigger than P of F3. We would like to be able to order the probabilities by somehow smoothness, and one would be over here, the other would be over here, and the other would be over here. This is the idea. So if we have to select a function randomly, probably this kind would be more probable than this one. But we want to allow this one because, for instance, in Kriging, it can happen that by some geological thing, all the strata is having this shape, and perhaps there is interesting, what's the name, gold things somehow mashed over there. So now we have three things: the space of functions, the space of realizations, and it could happen that we observe data. For instance, the prime could be x1 and 1. Here, as we have a Gaussian process, it's a scalar, x2 and 2. And now, what will happen is that we will select here, of all the possible functions, the ones that are compatible with these coordinates. So then we will have x1, x2, and 1, and 2. We have these points, and now, from all this space of functions, we will select the ones that are compatible with this. So really, what will happen is that we will have one that goes like this, another that goes like this, another that goes like this, another that goes like this. So here we will have an uncertainty, and the certainty is lower when we go to the observations. So then we have our first way of thinking into the Gaussian processes. There are some functions which have a prior. We will see at the end. One of the problems of Gaussian processes is that it's like Baroque altar. Have you seen a Baroque altar? Something like this, with lots of small histories over here. And the only way of looking at it, if you begin the study looking here, at this distance, you will be looking at every detail, which is what happens when you look at the book of mathematics. In the book of mathematics, you will have, the Amundsen or the others, they will go but which is the only way of looking at it? Going 10 meters over there and looking at the whole picture. So the problem is that we will go into the small details, and afterwards we will have to go back and look at it. That's one of the things that we will find, is that this idea that we are getting things here, and here we will have flexibility, will be introduced by a small thing over here that will give sense to everything, and it will be the kernel trick. Okay? So, of course, one possible function may be this one. Yes? But of course, we have introduced a prior, so this one will be highly unlikely because it's not smooth and yeah, but it's compatible. So that's one thing that we would like to do. We would like to introduce a prior on how things are flexible. And we will see that there's a trick. I mean, we will remember that I said that there are several tricks. So, now that we have this thing, we will define a Gaussian process. Gaussian process is a process where we have this thing and we have x plus, which letter I used, mu, and the difference between x plus mu and fx is distributed as a normal with depends on the distance. That's where we will introduce the smoothness. I mean, the distance between them, this distance, it will be a random walk, and this distance will be a normal Gaussian. And that's the assumption that is introduced. But one of the interesting things is that you can, even though this difference is normal, we will be able to introduce here ways of dealing with things that are long tail. Long tail means that, for instance, we might be able to, by playing here, we'll be able to use Levy-Mandelbrot distributions. The Levy-Mandelbrot distributions are distributions that do not follow the law of big numbers. That means the variance is not defined, which happens in the stock exchange. The stock exchange is fractal and so on. Well, the Gaussian process was invented several times, at least two simultaneously. It was invented by Einstein, and it was used for diffusion. So the diffusion of the variance is proportional to the distance in time. In the Bachelet, in his PhD, that coincidentally was 1 year before or afterwards, Einstein did this in diffusion, did it for the stock exchange, and he's assumed defined this diffusion equation for the stock exchange. And here's the trick point, is distance, the key point. The key point is distance. And that's the place where we will play. And we will define a distance that is adapted to our problem. So anything that you index them by coordinates, and you have two coordinates, and the difference in the output value is somehow a random process that depends on the distance, anything like that would be a Gaussian process. And we will do tricks with the distance, and we will adapt it to our problems. So there's a preliminary thing, because it will be part of the trick that will allow us to do interesting things. Okay, we have this X, which are our observations. But if we create a new space, we could also still have a Gaussian process. And this is the idea. So now, once we have defined the Gaussian process, we have our our Baroque altar. And now we have a story that goes over here, it's the same, and then they cut the head of the same. If you go to Granada, you can see that is the cut head, and you can see the trachea and everything. So there's a point here where something happens, but you don't understand what they did here until you go over here. So that's now we will do this point here, and we will understand this point here when we get to the end. So this is the kernel, this is the preliminary to the kernel trick. By the way, kernel trick is the technical name. In all the books, you will find this name kernel trick because it's a magic trick. You take the rabbit out of the chiste. By the way, this is not working, isn't it?
It's working perfectly.
No, microphone.
You can remove it now. Yes.
Ah, yeah, that's what I want to do. Because I have to move.
Yes. Sorry.
Okay, so let's look at the kernel trick. We can create a function f phi such that we have x, which is or d. By the way, Gaussian process is a process where the function is indexed by a scalar, the value. Gaussian field is the same, but with a vector. So we have this, and we will go into phi of x, which will also be a vector, which is like this. By the way, all of you know this notation of a slash under the yeah. By the way, do you know where it comes from? It's a very interesting origin. The physicists normally use this thing, but when you have an Olivetti typing machine, you know the typing machines, the old ones. My mother had Underwood, which was 10 kilos and like this and blah blah blah, and it goes like this. So in those you do not have this, but you have the underline. And this notation comes because of the restrictions of the machines. And of course, a matrix is a vector of vectors. So you put two straight because it's quite easy. So this is a vector. So now, if this is bijective, or sorry, if this is injective, Gaussian process here will continue to be a Gaussian process here because we will somehow distances here will be over here, and this can be anything. As a matter of fact, we will have n equal infinite because infinite is more nice and more scientific and lots of things. Anyway, so we will when we are playing with the math, sometimes we will be here, sometimes we will be here, and we will assume that they are interchangeable. I mean, we can work with this or with phi, and always a phi will be and a phi could be lots of things. For instance, this is not over there. Why we would like to have something like this? For instance, imagine that you have A and B, and you want to separate A and B with a plane or a line. How would you do it? It's impossible. You do it like this, like this, like this. You cannot separate A from B. So you have this one, this two. But what happens if you here create a new variable which is x3, and it's equal to x1 squared plus x2 squared. So let's something, whatever you need. You could do this. Now, in this space, this goes like this, and now you're able to separate A from B with just a plane over there. Yeah? So if you're on the plane, you are all in B. If you are under the plane, you are in B. Okay? So now, phi is equal to x1, x2, x1 squared plus x2 squared plus whatever you need in order to get the parabola. So this could be anything. And that's interesting, and that would be interesting for Hessian. You can tailor this thing to your problem, this phi. If you know about how your tech goes, you can introduce it to the phi. Okay, where I have it. So now we have a design matrix. Which is X. And we will define it like this. By the way, if you have questions, don't hesitate in asking. And this is a matrix of dimensions D. This is a matrix. And of course, you could have the phi matrix, which would be a vector also of phi1, phi2, phi(n), and this matrix now is of n times n. And we will play either with x and phi, because there's a function that for every point here gives exactly 1 point over there. It's not necessary that it should be bijective. Just that 1 over here goes to 1 over there. There is not something like this. Yeah, it could be as well. Anyway, by the way, we will make it interesting. So n potentially could be infinite. And in this phi, we will introduce information that is related to our problem, and we will see how to do it. So now our data can be expressed as xi or phi I. So it could be either of them, and we will play it. So now we will begin with the linear approach, and you could say, "Come on, you have made a distribution over all the possible functions, and now you go back to the linear." You're no, because there's this phi, and then afterwards we will do the magic trick. We will take the rabbit out of the hat. Remember what I said. We are in the metaphor is a Baroque altar. You know an altar? An altar. Fojiao the.
Sorry.
Yeah, you know Fojiao, you have a. Yeah, you have lots of little histories over here. Well, you have the same thing. Now, here, we will have introduced here in this history, we have introduced phi. Okay? And then we say, okay, now we will be linear. You say, come on, you have introduced an infinite thing and now we go back to linear? You're kidding me? No, because afterwards we will be linear, and then the trick. We will take the rabbit out of the hat and we will go back to the infinite possibilities of all the possible flexibilities, smoothness, and whatever. Okay? So that's the trick. By the way, that's one of the things that, at least for me, was difficult the first time I began with this, because I began and said, hey, what they're doing, and then now it's infinite. There's a kernel. Where did it come from? It comes because there's this thing here. So now we have done a mapping, and we will go to a linear model. Remember always that this linear model will be a tool for doing the magic trick of taking the rabbit out of the hat. So let's begin with the first approach. Oh, by the way, linear models, when you're in space of infinite dimensions, have very funny properties. Very funny properties. A linear function is continuous. In the space infinite, you could have linear functions that are not continuous. And the funny thing is that you can show it, but you cannot find anyone. So that's and that was what that was shown by Banach. And Banach was the one that is a national hero in Poland. So perhaps our friends in Poland can send us an image of the statue of Banach. And he had several professions. He was a mathematician, and in the year 43, the Germans decided to kill all the people that had a university degree in Lodz. Well, it's in Polish, so they have accents in the consonants. But there was a German that knew that he was the most important mathematician at that moment in Poland, so he just told him, come here, come here. And his second profession was giving blood for making vaccines for typhus. So his mathematical expertise was put to sleep, and he had a box over here full of fleas, and the fleas were sucking his blood, and those fleas were used for making vaccines, and that's how he survived the war. You have always to... Anyway, the linear model, which could be in the infinite dimensions. Here we have our national heroes, our other heroes. They appear in information. Anyway, the justification. This one. The justification is that we will have a rabbit, and we'll take it out of the tube by E. Our model is f of x is phi of x transpose w. And W is a set of weights that will give us the approximation. So this is a vector of weights, which will give us the linear combination that will give the approximation. And this is normal of 0 sigma n. This is the typical linear model, and I insist, although you could say that this is smooth, it might not be smooth, because this is a polynomial of degree 27. A polynomial of degree 27 would be something like this. So really, although we can think that this is smooth because it's a plane, it might not be, because this could be a very big polynomial of very big degree. So here we will go, and we would like to estimate. We will estimate W by maximum likelihood. Okay, likelihood is a substantive, so it's a name, it's a likelihood. But we will see that we will small likelihood of what? That's one of the problems of statistics is that you begin with likelihoods, and after 3 or 4 exams where you have to memorize lots of things that you do not understand, you use the word likelihood, and you don't know likelihood of what? Likelihood that you will fall, likelihood that you will pass the exam, likelihood of that the professor dies in whatever. What? Now let's look. Before we go into the details, I want to comment a few things which are important in order to use this thing. We will have the probability of the observation given the input and the weights. Oh, sorry. The probability of the vector of observations axis given the that training data and the weight. By the way, this is something to remember. Here we have a vector, and here we have a scalar. Remember that Gaussian processes are things, Gaussian fields are things that take a vector and return a scalar. So now we have this thing, and before we do the break, I1, I1, is I1, W. So this is the likelihood function. It was defined by Ronald Fisher, which was the man that formalized statistics at the beginning, in the middle of the beginning of the 20th century. But here, just at the beginning, we're doing something which is a geometrical mean. So what are we assuming? We're assuming several things. First, before we continue, because when you are going to apply Gaussian processes, you have to know which are the basic assumptions, because remember, this is an altar. Somiao. Fujao Somiao. So there are 273 stories over here. So here we have already done how many pages? 4 pages. Now here we're doing a hypothesis, and then we will continue. Like likelihood, it's used for so many times that you have forgotten what it was. And then here we will get a formula. And this formula is only valid if the assumptions are correct. So here we have the independence assumption. I am not sure if when you're doing Kriging in order to do the vertical tech, you can really, this assumption is correct. That means that if you have a GPS detector here in the UPC and another in L'Hospitalet, you cannot say that they are independent. Or yes, or you have to be just be conscious. And there's another thing. When I was a student, people from this department introduced a new pedagogical technique for evaluating the students. Instead of the arithmetical mean, they use the geometrical mean. This is a geometrical mean. They only did it once, because if they had done it 2 years, there might have been a Holocaust in the department. Okay, what happens if your marks are 9 and 1? An arithmetical mean says, okay, you have a 5 and you pass. Geometrical mean is 9 times 1 square root 3. So what is telling you? Here, in the arithmetical mean, this is the geometrical mean, the arithmetical mean means nothing happens, you just mix them. Here, it says all of them have to be high in order to get a high value, simultaneously. And this is what we have in probability. Here, we are saying, and that's something that you might change by tweaking your program, we're saying, okay, probability, product of probabilities is intersection of sets. And in logic, this is prob, this is set theory, and logic is an and, logical and. So you're saying, okay, I have a score, and this score is that one and the other, and the other, and the other, and the other, until you have n are well modeled. If only one of them is badly modeled, everything goes down. So that's a very strict thing. It's just saying, imagine that you have 9, 9, 9, 9, 9, down, 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 and then a 0. So that is a limitation of maximum likelihood. By the way, in my PhD, I just worked with, I just looked at them, and when there was one that was bad, I just killed him and I didn't use it. It would be just like, okay, you can select of all these exams, which one you leave out, and then someone would say, okay, I leave out. So that's one possibility that you have to take into account when you do maximum likelihood. Evaluate each of them. If there is one that is very, very bad or very different from the others, you just throw it away. So all of them simultaneously have to be correct. Now we go here and we introduce the model. Introduce the model. And our model would be Gaussian. Oh, by the way, if you're using my papers, there's missing an I here and a square here. Because this week has been a very tough week. Every day something appeared. It was like, and there's someone really laughing. Oh, by the way, in order that he feels very guilty, I would say that I wanted to write this in again, so it would be clear and without and everything, but I have no time. I'm joking, yeah. Okay, now likelihood of what? Fisher was a very intelligent man and also with common sense. Okay, here is livelihood. Our model says, okay, there is a deterministic dependency between the input and the output, and noise. So here, we are assuming that our model is likelihood that what? That our model is doing the work correctly, and we only see the residual error. So likelihood of what? The model is correct, and we only see the residual. And I could do like the, okay. And of course we are in the linear, this somehow is saying, okay, it's a linear model, but take into account that this phi could be a polynomial or whatever. Yeah? An exponential, hyperbolic cosinus that makes it more scientific, whatever. So, okay, now that we have this thing, we will operate a bit, and after a bit of operations, we will go into one divided by 2p sigma squared n. And oh, by the way, the n here, it means noise, and the n here is the number of samples. I suppose the Chinese don't have these problems because they might have a special character for everything. Now we will have only sigma n quadrat and image phi omega. And this is and this here is t, and this is y. And now we will have this set of operations. By the way, from now on, I will continue making these pictures because it will allow us to understand what is happening. Really, here you have a dot product, and if you remember, that product is proportional to the cosinus of an angle. So, if two things are parallel, they will be understood as they are similar. If they are orthogonal, they are not similar. Remember that the key idea of the Gaussian process is this one here, and there is a distance. And this distance will be a similarity measure. Okay? So, this is a good point for a 5-minute break, because now we will go into heavy stuff.
Okay. Thank you. So we make this few minutes break. So we maintain the connection on.
We maintain the connection. Should we phone them in order to tell them that we have finished, or?
Likely not needed. Unfortunately, we cannot share some coffee and water here and pastries.
Okay, then I will be 5 minutes, so that means that at 11:10 we begin.
Okay, perfect.
Thanks. Now I will have a bit of coffee. By the way, any comment or anything? Feel free to ask or to comment, and as a professor of mathematics, if I say something that is not correct, please tell me. Yes.
Okay, so let's
go. Now we will have a bit of coffee, and we will have more coffee. Oh, please finish. Anyway, what I was going to say? Yeah, at the time of Banach, they worked on Saturday mornings and they did classes on Saturday mornings, so they were more ¿cómo se dice? Trabajadores.
Hard workers.
Hard workers.
Yes, I have a question in the meantime.
Yes,
You
tell me.
because you commented that, I mean, in the application that we have done, your question before about independence, right?
Yes.
That we are doing is applying about the receivers. We take, we are not, I mean, we apply Kriging on the receivers regarding to a good boundary. And we make the first computation of the interpolation of the field model of Vitek values, and we remove from the observations, and so we interpolate the receivers. So the receivers, in general, quite, I mean, we have removed the functional dependence before because it's complicated, and we are working with receivers which should be quite zero center and maybe relatively independent.
And there's
Fully independent. Somehow.
Yeah, there are two things. One is that, so that means that you're doing it correctly. And the other is what I was going to propose that will help Asia to deal with the fact that you're with, in a three-dimensional space. So we can decorrelate and whiten. And we can introduce the whitening process inside the estimation, the Kriging estimation. And I think that you will like it because it was inspired by the Lorentz contraction.
So everything is going up and down.
Yes. So, we will introduce a Bayesian prior over the weights. And now, here, it's a crypto prior, because it seems crypto means hidden, like a crypto communist or crypto whatever. Crypto communist is an agent and a spy. A crypto prior, in the sense that we are saying, okay, we will only accept certain slopes because it's over the weights. So it seems that the prior is on the slope. So, but we want to do, remember that we had this thing here where we had the line, we had the parabola, and here we had something like this, and we had this probability of the function. Okay. Indirectly, we will be working in this space with infinite flexibility, even though we're introducing a prior on the slope. So you might think, hey, if I put a Bayesian prior on the weights, you could say I am only dealing with these functions over here. But it's not true, because we have the phi. And the phi will allow us to take everything into here. Get the idea? Anyway, at the end, we will have a mystical way of looking at things and we will see the light. Anyway, this is a crypto prior over the weights. And we'll say that the prior over the weights will be that the weight will be distributed as a 0 sigma p That is that it will be something like the probability of this distribution of the weights. This is the weight space. Now, this is not the metaphorical space of functions which are ordered. Hello. I am sorry, but if you have questions, perhaps afterwards we could ask, we'll talk, or another day. Or if those of you that if today we have gone too fast, perhaps we could repeat this seminar another day again, so we can digest it better. Anyway, it could happen that the priors, the weights, could have correlation, and we will say that perhaps we will admit that the weights have a correlation, and it might have sense, and we will see why. And now, I mean, it could be an ellipse, which are the full covariance matrix, a Gaussian with a full covariance matrix, and the axis of the Gaussian will come. Oh, this is a zero. Sorry. Okay. Or like this. Anyway, here we will introduce prior information about the problem, and we will see why. This allows for the introduction of prior information about the problem. So, this will be interesting because we will be able to introduce what we know about the problem from two directions. One direction will be of the prior over the weights. Note that if we are working with phi, potentially it could be that we could have dimension infinite or whatever we want. So, what we have? This is the Earth. So we have three coordinates, x1, x2, and x3. x1 and x2 could be latitude and longitude, and x3 could be height. And over the Earth, we want to do Kriging over, and this is the problem, this is the VTEC. At different points, different coordinates, we could have
electron density, right? Electron density.
Tech, sorry. The electron density. Okay, electron density.
Yeah, it's good.
Sorry. So the electron density is on the space of dimension 3, and note that now, given a coordinate x1, x2, x3, we want to know this f of x1, x2, x3. So this is a way of depicting our four-dimensional problem. That means we have the three coordinates, and at each coordinate we have a function. Well, sorry, at each coordinate x1, x2, we have a function that goes up, and we want to somehow, by means of Kriging, interpolate what we would have in between them. So, by the way, Gaussian process means that the variance depends on the distance. So probably if we want to estimate something over here, a certain point, we will use them, and we'll give more importance to these ones than to the ones that are further away. So now we have this thing, And there could be a correlation. We have two different things. First of all, of course, we're in Europe. I suppose that in China you could visit it at the center, because China, in Chinese, it's the country of the center of the world. But we're here, so here we could have the ionization like this, no? So probably you would like to take care of the fact that the world, the stations, have a certain spatial distribution, so there will be a correlation between x1 and x2. I mean, these functions will be over here, but the stations probably will be like this, and here like this, and in Japan in a diagonal. So there's a correlation between 1 and 2. And also, there's another thing that the dimensions are different. I mean, here you could have x1, x2, very long, very big values, and in this direction, smaller values. For instance, these are kilometers, these are kilometers. Perhaps these can have big values. So we would like to take into account correlations and discount dimensions. That is, for instance, from here to here, you could have 600 kilometers. When you go up, probably this is about 150 kilometers or 100, between 150 and 450. And if you go over here, you could have 6,000 kilometers, and probably it will be different. So we would like to discount the dimensions, and we would like to take into account the correlations. There are two things that we would like to introduce, and somehow we can do it by means of this prior, because I don't know, if we're in American university, we would have things that go up and down, and because if instead of working with phi, we work with x, which afterwards we will use phi, but anyway, of course, if you have this thing, perhaps if these two, they are correlated, you would have to take into account the fact that perhaps x1 is approximately k times x2, so these weights, depending on what you are doing, might be equivalent. Also, it could happen that this is 1,000 times bigger than this one. So the weights over here should be smaller than this one, so that they will have the same contribution. Because if the importance of going up is as important as going horizontally, these two might have, and you want them to have the same importance, these weights should be smaller than this one, so that they will have the same importance. If this is 1,000 times bigger than this one, and you want to, and they will have the same order of magnitude, perhaps you will never see what is going on here. Yeah? And also you could have a dependency. So, we will do it by introducing this sigma, and this sigma will give us correlation between the three dimensions and somehow which should be shorter and which should be longer. Yeah? So, this is one point where we will be able to inject our prior knowledge of the problem. But there will be the kernel trick. Instead of X, we will use phi, and funny things will happen. So now let's continue. Now that we have everything more or less defined, we have defined our prior, we are able to look for the probability of the posterior which will allow us to select from the infinite possible functions the ones that are compatible with observations and with what we think that the way they should behave. By the way, is it scientific or not? Science is objective, but we're introducing what we think it should be, so that's subjective. But anyway, if it works, it's good. Distribution of the posterior at a test point. Now, the test point will be called X star. And now, before we go into the geometry, and we will do some geometry, we will do some algebra. Now, I hope that you will not be traumatized. Now we have Y star, which is our forecast, and this is phi X star transpose times W. Now, that's important. This is a test, not random. And this is random vector, and this is a random scalar. It's important to remember, one of the things that happens when you have lots of equations is that you forget about what you're using. So here we have a vector, and we get a scalar, and this scalar, so this will be a one-dimensional Gaussian. And this is not random. Sorry? It's a phi.
The dimension is 1 multiplied by n.
The dimension is the dimension n. So here you have X star, which is of dimension b, and you go like this, and phi of X star is n. And W.
But what star is a scalar?
No, sorry, it's a vector. It's an observation vector. It's an RD. For instance, it could be
Position, right?
yeah, the position. It's 1, it's 2, it's 3. Here we have the Earth, and here we have this, and it goes like this. So it could be this.
Let's say that.
So why this is a scalar, not a vector?
This is a scalar. This is a vector, because it's our forecast.
It's electron density, for instance. Y will be the electron density, or the residual of the electron density regarding the previous model Y. X will be the position vector, where we want to interpolate to fill all the overall atmosphere with all estimation of electron density. BOP will be the weight. So the weight should extend to a certain number of neighbor values, observed values. So you have 3 numbers. 1 for the magnitude, or if I am wrong. 1 for the magnitude to interpolate, it's dimension 1, y. 3 in the case of the problem of the electron density interpolation sleeve for the 3D problem. So it's the dimension of x. D, the uppercase D will be 3. BW, the dimension of BW will be depending on the number of samples, let's say, taken to
No,
right?
it depends on the dimension of phi. For instance, now imagine that phi is identity. Okay, I will do it with this example. It's a good thing that you ask and the others do it, please, because I could think, oh, that's trivial. You know the story about Wiener? The filter of Wiener? How many of you have done Wiener, filter of Wiener?
I've used it.
Okay, he was a very special professor. And Paulos, there's a journalist, a mathematician that is also a journalist called Paulos. And he has several books about the mathematical alphabet and the mathematician that makes jokes. And he says that he was in class, and then Wiener wrote a long equation and said, that's evident. And then one student said, I don't see that it's evident. So he went on looking, and then looking, and just went out, and went around, and 20 minutes later came and said, it's evident, and then continued. So,
this is not your approach, right?
No. So that's why I want you to ask, because perhaps I think it's evident and it's not.
It's a typical dot product. It's two vectors, so it's a typical dot product.
This is y.
So like in master should be dimension factor. Well,
This is,
you can map from the D space to N space.
These approximately 2
Yeah.
Here we have this point that has coordinates is 1 to x3. This is the electron density, and we approximate the electron density value by the scalar dot product of the coordinates with the weights. So these will have the same dimension of this. Here we're assuming that phi is identity. But afterwards we will take the bracket out of it. Yes?
Okay, I understand now. Yeah. I certifies a matrix with many observations. So here, vice versa, just one observation.
Yeah. Sorry.
Yeah,
this
that's
is a
why-
star.
why I'm confused. Yeah.
Star. Yeah. No.
Yeah,
Please ask.
vector, not matrix.
Oh yeah, don't worry. We will have the apotheosis of matrices. Okay. Now, we would like to have the distribution of this y. And so now we will compute it by a Bayesian approach. That is, so in order to get this, we have to have the distribution of this because this is the test, it's not random. So what we will do is that we will find the distribution of W, and afterwards we will multiply this random vector by a constant vector, and we will get another random variable. So our first approach, first we compute PW on X so that we'll compute this, and afterwards we'll compute this distribution, because this distribution will be the distribution of the projection of a random vector. This is a random vector, and we'll project it, and we'll get this. Okay? So that is, and then we will compute this given x star x and w. And this will be trivial because it's this random vector multiplied by this constant vector. And anyway, we'll do it. So now we have PW given. By the way, you have the equations in the notes. This is this. And this is very difficult. And we will do a trick because it seems that statisticians are professional magicians. And this is very, very difficult. By the way, do you think I'm joking when I say that statisticians are professional magicians? Look at Wikipedia and The Economist. I have used several of his papers, and he's a very good guy, and he's a professional magician, of course. Really, he's a professional magician, and even has made a mathematical machine, mechanical, that throws coins and gives exact the value by solving a differential equation of how to get a phase or whatever. Anyway, this is very difficult, and we will use a trick. And it's a nice trick because this, if we compute only the upper part, this is proportional to So now we'll go into the professional magician thing.
It's the second x will be a little bit.
Yeah, it's a little bit. Thank you. And of course, put all the underlying things like that. So now we have this thing, but this is a conjugate prior, and a conjugate prior has the property that Gaussian that has a conjugate prior that is a Gaussian gives a Gaussian. And then you get this value. If you have a Gaussian, the value that divides is 2p times the determinant, and there's a square somewhere. So anyway, this is a multivariate Gaussian. And then the denominator is so we have this thing. So it's not necessary to compute this thing that is very complicated. Once we know the variance, we will know the value of the denominator, so it's not necessary. So now comes the Diaconis. Diaconis was a professional magician, and after a few, like about one complete blackboard, whiteboard, you get this. So now here we have the inverse of the covariance. And here we have the mean. And then, so here is the database. That is the X, the database of observations. This is the targets. And here we have the process database by phi. Once we operate a bit, we get that the probability of the weight is there's a mean, which will have a very special form, the covariance. This is here we will introduce the trick of leaving out the linearity by means of this. So the covariance of the weights are the prior, the covariance of the data, and the weight that mixes them is the noise. Note that if the noise is zero, sorry. Yeah. Sorry, if the noise is zero, this is infinitely bigger than this one. So you use the data. That means that you have something that has no measurement error. If this is infinite, that means that your data is useless, so you use the prior. And you have the mean. And this mean is the one that we will use for doing the interpolation with the data. And we will see that it will be a bit tricky. So now we're still here. We have this. Oh, by the way, this is Gaussian. So we do not need to compute this thing because we know that this will be the thing that divides. This expression will have this form where the sigma is this thing in parentheses. So now be prepared. Because we have W, the mean is sigma phi t. And for those of you that have done Wiener filtering, remember? No telecos? Sí, no telecos. Wiener filter era A igual a R x R z. This is this, and this is this. So really we have the Wiener filter. So you could say, come on, you've done something very complicated in order to repeat the Wiener filter that we were able to pass some years ago in a very nice subject. I mean, you have enjoyed signal processing. Bagada. You like it, but I think that our students don't like that subject because it's, they don't need to do a geometrical mean. Just a normal exam kills everybody. Anyway, now we have this structure, but we want this one. And once we have this, we can compute the output, which is the y star. So y star is phi star transpose W. Now, in order not to write too much, phi star means the value of phi at x star. Yeah? So here we have something, and now we will see what is going on. We want to get this one. This is a random thing, this is a constant thing, and this is a scalar, which linear combination of Gaussians is a Gaussian, so it should be a Gaussian. So now the mean value of this is the mean value of this is a constant, so goes out, and then we have this thing. And then this is a scalar, so it's a variance, the covariance, and then we have that this is WT phi star, WT phi star, and after we get phi star quadratical form. And this matrix is this matrix here. So now we have that the output is a Gaussian that has a mean value that has this form and a variance that has this form. By the way, this variance is something very interesting because one of the powers of Gaussian processes is that you have this one. In normal linear filtering and machine learning things, you don't have this thing. And what's this? When you have this thing here, and you have, remember that we have, okay. Remember that we have some fixed points and a universe of possible functions. So the universe of possible functions would be like this. Yeah? So in observation points, you have this fixed because all the functions that you select go through these points. And all the others, the possible values, will have this. So this will tell you the uncertainty that you have at each point. So that's important. This is the uncertainty that you have at each interpolation point. And that's important because you will know how well you're doing. I mean, and that's one of the strong innovative points of Gaussian processes. Gives uncertainty at test point. And it comes for free. And that's a good thing. For free, you know how well you're doing it. So that's one of the things that if you are going to give values of Kriging, you can also give a confidence value, which is what makes it useful. So once we are here, we will begin. By the way, you see all these things here? They look nice, don't they? Of course, you will not ask me to write them on the blackboard. It's just mechanical. Just a chimpanzee that knows the rules can do it. So I have just written it here so that if you want, you can be sure that I'm not lying or anything. So now once we have these two things, as this is the projection of a Gaussian value, of a Gaussian random value, we can get the value of the distribution of the interpolated value. Oh, by the way, the interpolated value, A will be the mean value, and B will be the variance. Okay? Habías acabado tu limite? Ou poder continuar a fazer? Ou continuar? No, no, depende dos outros, sim. No, because there's one of the things I wanted to do is I wanted just to get the algebra, because the important thing is the geometry of the algebra. So now we have the probability of star given phi star given phi given y is our normal. Phi star t as 1 phi y phi star t is 1 phi star so remember we have this case here. If x star is here, what we have is the mean value and the confidence value. And now we will have
there is a missing the noise
variance.
see. Thank you. This noise variance is important because when we begin doing juggling, it will, then something will disappear. Have you not seen it? Okay, now we have all this comes because the kernel trick comes from this A, that is this A here, without inverse, A is here. So somehow it's a mix between the covariance of the data and the prior on the weights that indirectly are priors on the data. So now here comes the top and the trick. This can be understood in two ways. We can express the problem as phi t covariance matrix or as a Gram matrix. So here we will do a bit of magic in our very long history of the altar. We will do a jump. We can either work like this, which is the Wiener solution, or we could go here. Note that by changing the transpose, we go from d times d to number of samples times number of samples. By the way, for those that have done functional analysis, this is working in the dual space. And here will be the place where we will do the trick and we will be able to introduce whatever similarity distance that we want. So we will go from here to here. And going from here to here is this. Is the next transparency, is the one that has the one here. I will not do it. You will believe it. By the way, you remember what I said about Wiener and it's evident? In the book Gramundsen, it said, blah, it's evident. And it took me about half an hour to see that it was to get this. So you just believe it. Now, we can express the problem either like this or like this. This here is A. But we would like this one because here is where we will have the Kriging. And we will be able to introduce this idea of similarity between points. But we will see that the intuitive idea of similarity will be a bit richer. So then we have A, our forecast is this thing here. By the way, you have this in the notes. Or this one that is more elegant, and is the one that so, if we look at the problem from this point of view, we have this forecast. If you look at the problem from this point, from the grand matrix point of view, you have this thing. And this is a dot product. And this is dot product. And but with a matrix that is somehow introducing the geometry of the dependency between the elements of your problem into the dot product. This is, how many of you have seen this as a dot product? I mean, you could have xty or xt a matrix y. Here we can introduce a geometry and adapt the dot product into the geometry. For instance, in a problem, perhaps we had a special dependency between x1 and x2, but not between x3, so we could introduce it here. And also, this is a dot product, and this is a Gram matrix. With a W in the middle. By the way, what happens if, for the necessities of our problem, phi goes from D? Is this D, because of the necessities of our problem, is infinite? We will not be able to compute it because that means that we are doing an infinite dot product. So we will have to do it indirectly. Also, it could happen that this is much bigger than this. I mean, if you have a small number of points and a high dimensionality, this could be a problem. So the nice thing of Gaussian processes is that it works with this expression, and it has a geometry that it will clarify the geometry. So before we begin the final, it's the Everest. If we are doing the metaphor of the Everest, we have and we are in the base camp, so we will sleep a night in order to get early at 5 o'clock in the morning, going up and going up. So now we will do a 5-minute break before we do the big going up. By the way, the big going up will mean that we will be able to depict geometrically what is going here and what is going here. And you will be surprised of what is hidden under these symbols. So now we will get a bit more coffee because now, oh, by the way, this part here is soporiferous, that means anesthetic, but what we will be doing here are geometry. So before we go into the geometry, which we will do a small break, and I think that we will finish by 1 o'clock. Is there anybody that has, everybody can? Tu pots? Bueno, quan hagis de marxar no et faci tall i ja... És una llàstima perquè ara ve la part... Okay, so 5 minutes of break.
Okay, thank you. So we continue in 5 minutes. Keep online.
Bueno, en tot cas, la idea és, la part és veure el truc que farem aquí. És clar, és la primera vegada que ho faig així, sinó que no com temps.
Energy too.
No, he sentit el cafè, perquè això... No. Espera que no. Aquesta? Sí. Vale. Gràcies. Bueno, gràcies per haver vingut. Espero que... no sé si ho digerir, per exemple. Molt bé. Gràcies per venir. No, però ara ve la permaca. La permaca és què està passant aquí. I veuràs que és una semblança de semblances, una transitoritat de semblances. Em sembla, si m'ho permets molt bé. Que és la procediment és la probabilitat de la distància. Sí, en el temps o en l'espai. Dos punts on hem de poder introduir la informació que sap de com estan distribuïdes les funcions i com pujar el valor de les Bueno. When you were playing with him, yes. Basketball. Oh.
Sorry for that.
I'm sorry for the officer. But then if we repeat it,
You need to apply.
because
I don't know how.
you also
No.
It's more straightforward. It's more straightforward. Just say everything.
I don't know a lot about it.
You need to apply this
Não consigo. Aunque es divertido la charla, que cuando la tienes es muy funciona. Perché tu io quello che donava la gana perché era l'entropia, come era l'evidenza, es como Einstein, ¿no? Que era senza neutrons y pasaba de todo. Porque no existe, porque era Einstein.
¿Quién le iba a decir algo?
So now let's do the final clean to the. But there are 3 points. By the way, yesterday I was doing this thing, but I did not have time to put it in clean. It's A, B, C. But so now we will work with the. ¿Has conectado el audio? ¿Has conectado el audio? Sí, has conectado el audio, pero sí. Vale, gracias. Okay. Now we will work with the Gram matrix, but before we go with the Gram matrix, let's really do a recap of concepts. The key point is the meaning of dot product. So you have 2 things. You have the semantics and the syntactics. The syntactics is just the symbolic operation that can be done by a chimpanzee without understanding. The semantics is the meaning, how you understand. So you have this thing here, and this is a distance. I mean, if this is small, that means that they are near. And this is this plus this, we all know it, but I want to have a word in order to say what is going between this. So this distance is small when this is big. If this is big, this is abstracting, so this is small. Okay? So this will be similarity. Of course, you would say that's a tautology. No, the meaning of similarity is because afterwards, whatever is a measure of similarity that behaves like this will be good. So we have a dot product, and afterwards, the key point, the rabbit, will be just introducing another similarity here. The other thing, we have this dot product here. So this is A. Now let's go to B. The product of this kind is T W P Y. What is happening here? This is a dot product, but a very special dot product. We can here do the singular value, the eigenvalue decomposition. These are the eigenvalues. Should I explain it or not? So now, given this thing, no, this is not necessary. I'm sorry. I have this thing, and now we will look at this afterwards. This is the ellipsoid related to sigma p, and here we have 1 lambda 1, and here we have lambda 2 v2. So these are the 1 lambda 1, lambda 2 v2 are the eigenpair of sigma p, are the eigenpairs. So what we have something interesting. If we have I sigma p with I, this is ube I times lambda ube I, this is lambda I. And if we have j t sigma p ube I, here we have 0. So this dot product is a very special dot product. If these terms are parallel to one of the eigenvalues, then we have that eigenvalue. And this is interesting because somehow we're introducing the metric. Imagine that somehow we're in Japan. This is Japan. The stations are aligned in 44 degrees. So probably, if we compute the ellipsoid that encompasses Japan, it will be like this. So Japan will have a covariance matrix with a lambda 1 v1 that is big over here, lambda 2 v2 that is small over here. So now, what happens? If we are going to compare to the dot product between two stations that are like these, probably the dot product with the sigma, which is the sigma, will be high. And if they are like this, the dot product will be small. So somehow, in this dot product here, we're introducing the geometry of the system. So this is the meaning of having this dot product. This dot product, somehow, if they are both aligned with an eigenvalue, you have an output that is proportional to the eigenvalue. If they are orthogonal, then you have something that is 0. Okay? And now the last one is the geometry of an ellipsoid. By the way, this is important. When we have this thing, we have to think on similarities. And here we have introducing that. And the other, I know what I say, A, C, B. Geometry of an ellipsoid. And you know this, no? This equation. This is the equation of an ellipsoid. Well, this, if you have xt sigma x, you have also an ellipsoid equivalent. So this is one thing that we will use. So now, in the next 45 minutes, we will use this idea, and somehow, if we have time, we will introduce this idea of the dot product, because we will be able to inject our primary information through either the dot product or through the similarity. So now, let's try to understand this, which is the question with which we will work. And then we will have this document. And we will see what will happen with this equation. And this equation has a very special okay. First of all, what is happening here? Impressive equation, isn't it? I mean, you go in the metro in the metro, and you have this, and people will say about this. But now let's look at the structure. Structure of B. This is a vector. It's a dot product of a vector with a matrix. So this Y star is something like this. Now, this is the inverse of a matrix. So this is like this, and now here we have I. So if we do the dot product of this with this, we will have a scalar. So this will be a vector times y. This times this is a scalar, this times this is a scalar, this times this is a scalar. By the way, this is a dot product, which is the meaning that we were giving to a dot product. A similarity. We'll look at the similarity of this with the columns of an inverse matrix. This is absolutely abstract. We will see that no, it's not. So when we have this is alpha I, where this is this very complicated thing of this type, this thing, with the column of inverse, yi. We have I equal 1 to n. So this x star is a linear combination of the i's. And this, what should we ask for this alpha? With an intuition of what is going, not this is a dot product, similarity. Where similarity, here is a similarity, here is a similarity, it's the inverse of a similarity matrix multiplied by a similarity vector. So what should be the coefficient? Similarities. So here we have similarity of x bar with x bar, which has sense. I mean, geometrically, if we have this here we have a point. And we have this one here. And we want to construct this one. This is x star. Do you think that it's reasonable that if this is similar to this, to this, to this, these three that are around this one should have an alpha, a bigger alpha than these that are far away? No? So really, this is alpha, and this alpha will tell us a similarity, but will be a very special similarity. Now, our cloudy way of thinking is that this is a similarity of a similarity, and this is a matrix of similarities, and we get the inverse of a matrix of similarities, and we will multiply a similarity with a similarity, and we get something that is a similarity. But it will have several specific subtleties. So now the structure is a linear combination of tangents, which, and we would like that the ones that are around the place that we want to interpolate should have a bigger alpha than the ones that are afterwards. And we will use it because we're indirectly having similarities here. Yes? So, try to understand these similarities. What are these similarities? How do we get them? And we will see that it will be a surprise. It will be not so, because what is the meaning of the inverse of a similarity matrix? That's very abstract. And multiplied by a similarity between the, because this is the similarity between the points of the database, how each of the observations is similar to each other. And this is the similarity of the test to all the others. And this is the inverse.
Similarity? Maybe there is similarity?
No, but perché it's a transitive similarity.
Okay.
So now, in order to go down of the abstraction, we will go from phi to x. So now, in order to understand, we will have we will do this thing in order to understand what is going on. Afterwards, we will see that. Note that here we're saying, okay, this is diagonal, but of course it's a dot product, so somehow. And here we're saying, okay, there's no noise. So we get this, and also we're saying phi is the identity. So this is structurally equivalent to this one. Okay? So now let's try to understand the similarities, what they are, the similarities. So the first thing, A. Now, when we have this Gram matrix, this is the Gram matrix. What happens if we take one row and one column? Here we have its I, its j. So what we have here is similarity between inputs. If this value is high, they are very similar. Of course, you could say there's a problem. Going up will have a lower variability than going horizontally. But don't worry, it was taken into account with this one. Let's suppose that you have already normalized. But do you get the idea? This thing is telling you how each row is similar to each column. So it's a similarity matrix here. And of course, we will have to see what we have. Okay. So now we have B, and B is x star transpose times x. So here we have so here we have similarity of each one with each one. And here we have similarity of the test point with each of the observations. So now what we have here is x star x1, x star x2. So here we have similarity test versus observations. That is, we are going, remember what we are doing. What we're doing is that we have this thing here, pam, 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 pam. And we have so here we have the test point, and here what we're looking is the similarity between this and this, and in order to do what? To give this one a value that should be something that is gives, for instance, if it's here, the alpha to this one should be given more. This should be something. The value here should be similar, more similar to this one than not to this one, and this is taken into account with this. Okay, but also we want to this is in space. It's a bit more clear. So what we have that this is similarity, the test point towards the data point, and here is the similarity between the data points. So now let's go by approaches. Let's study this equation for different cases. And first approach. It's xtx is the unknown. Let's assume that the terms here are orthogonal. So the this gram matrix is a diagonal matrix. Let's see what's going here. This equation will be like this. By the way, now we are very near the final, the ending of the Himalaya. This is the verse of this, that equation has this form, and now this is the first approach. Afterwards, we will use a complete matrix. Now, what we have is that this is which is a typical interpolation equation. That means the value is how similar this is to a given input, and if they are similar, normalized by the energy, this should have this value should be similar to this one. If they are not similar, you should not use this one. But we are not taking into account the similarities between them. But by the way, this is a typical interpolation method. And probably, if you have to go very fast, it will work very well. But we're still in the, but we have not used the kernel trick. Now, let's go, so it's an interpolation by similarity. That is, if the observation is similar to our test data, we use the output value, you combine them, and that's the alpha. So the alpha will be how similar I is to the test. But now, let's go to the heavy stuff. Hey, what's the meaning of the inverse of a matrix? And here comes the heavy stuff. The heavy stuff will be this picture down here. Sorry, the final. But I think that we will finish. Second approach, it's the axis full. So, what happens with an inverse? We have A times A plus 1 is equal to I is equal to this 1. Inverse. And what we have here is this thing. What we have here is that if we multiply a matrix by its inverse, we'll have rows of the original and columns of the inverse of a matrix. And this should give a diagonal. So, if A1 is similar to the A1 inverse, have a 1. If A1 is different from A2, this column here, you have a 0. So, what is happening when you multiply a vector by the inverse of a matrix? It's a detector of columns. So, multiplying a vector by this is a detector of similar columns. And this is now the point where we are going fast, and the key point of the similarity idea of this linear process. If you multiply this with this, now let's suppose x1 is similar to A1 and A3. So we have x1, x2, x3. And here we have A1, A2, A3. If we multiply this by this, if this one is somehow similar to A1, very different from A2, very similar to A3, what we will have? This time times this will not be 1, but probably we will have 0.8. This is very different from this, we'll have 0, and if this is similar to A3, we'll have, for instance, 0.75. Get the idea? So, That's the meaning of the inverse of a matrix. Multiplying a vector by the inverse of a matrix will tell you how your vector is similar to the original rows, to the original columns of the matrix. So it's a detector. And that's what will happen. So that's the pattern of similarities that we will have. And now I will need space. Anyway, this idea, you've got this idea? So this is the key point. In order to understand because what will happen is that the Kriging is doing something more subtle than just looking to which is the nearest one. So I need the whole, we still have 25 minutes, but hopefully, now this is this. This era. Now let's see, with this understanding, what is happening here. First of all, this times this is the similarity between this and each of the input points. And this will be a detector of how this is similar to this one. So we will have a transitive similarity, a similarity to similarity that is related with a similarity to similarity. Hopefully with a diagram, the similarity so this will give us similarity of observation to train, and here detector of element of train that is similar to what? This goes to here and then is multiplied by here. So we are selecting which of the training test has a similarity pattern to the other similar to this one. Which is similar, which is similar to the similarity pattern of X. Hopefully I will be able to do the diagram and this will have a meaning. So this is how this is similar to this one. And this here is how this is similar to all the points. So a certain point is similar to all the others. Of course, it will be equally similar. Yeah. So this is a detector, and this is a sim. So now, after a bit of operation, we will have. By the way, this will be called similarity H1, similarity H2. And we will use this notation. How star is similar to 1, star is similar to 2, star is similar to n. So finally, we will get and this will be called like this. And now this is a bit abstract, and we will see the effect of this inverse with a diagram, and perhaps we will understand what is this detector. I mean, this is how a given point is similar to all the others. And this is how the test point is similar to each of the test points. So now, let's do a diagram. Ooh. Now, let's suppose that we have xk, and here we have x1, here we have x2, and here we have xn. So, what do you have here? This is an indicator, it's telling you how this is similar to each of the others. And now, x star comes. This term here as star is telling you how this is here. How similar to each of the others. Okay? And so, when we're doing this product times k, we have a certain value. Because this is how this is similar to this, how this is similar to this, how this is, and this is how this is similar to each of the others. So, what would happen if we, by lab, had another like this? For instance, Excel. The column of Excel will be how is this is similar to this, this is similar to this, this is similar to this. Now, if we do this dot product times, this has a certain pattern that is similar to K, but this has a certain pattern of similarity that is very different from L. So, what do you expect of this with the L? Should be small, and this with K should be big. And this is what we have. This effect of this times the inverse is telling you relative similarity between I and all the others and star and all the others. And this is one. So, it's telling you, it's interesting. What is happening is that if the pattern of similarity of this is similar to one of the elements of the columns, then we're going to use the target. If the pattern of similarity of this one to all the others is very different of a given that, you do not use that column is 0, so you will not use I. That's the meaning of the inverse. So it's not just similarity, it's just how you are with respect to your neighbors. So you will use the target I of the ones that have a similar relationship with the neighbors. And that's the key point. So, and now, but notice that I'm repeating all the time similarity, similarity, similarity. So everything, anything that we would think that is a similarity can be used for substituting the Dutch products. And that will be the kernel trick. So, we're nearly finished. Yeah, it's 10 minutes, so, but in less than 10 minutes, we will have the apotheosis. We will get up to there and we will be able to see the whole landscape. So, we'll need the blackboard. So now we saw what is happening. So now anything that behaves like a dot product and tells you how you're similar to your neighbors and how your neighbors are similar between them will be obvious. So generalize. The product general measure of similarity. Kernel tree. By the way, this is technically known as kernel tree. It's the so let's use one that is very common, and in the economists will use something different, but Gaussian kernel. We will see that a Gaussian kernel will be a similarity measure, so we could use it. So now we have this. So here, this is a constant, and this is the exponential of a dot product. So this could be written in this way. Before we continue, is this a similarity measure? Yes, because if they are similar, this is small and this value is high. If they are dissimilar, this is big and this value is small. And it will have have all the syntactical properties of a dot product. So as it has the syntactical properties, that means the manipulation properties of a dot product, we can use the semantical meaning of similarity. So now we have this thing, which is a constant, and this thing that could be developed in this way. And then now comes the kernel trick. And it's a pity that I will have to, but you will remember this one. Now, this is a constant times so I will not do it because yesterday I tried to do it by hand and it became a bit long. Here you have all the polynomial expansion products. You can transform this in taking this and taking all the possible exponentials and with different components, and it's a dot product. So now we have something interesting. All the things that we have done could be done by getting the x into an infinite space or whatever, or using this. So instead of doing an infinite dimensional dot product, we could use this, and all the equations that we have used until now would be valid. Is it too abstract? You're a bit tired? Perhaps I have taken too much coffee and you have not taken as much coffee as I have done. But do you see the trick? I mean, instead of we've been all the time doing this thing, but we could also use this thing because they are equivalent. And this is just a difference. And that's, by the way, this is one possible kernel. Rasmussen, chapter 4 has a library of kernels. I mean, here, this is a reasonable kernel for what Aisha has to do, but for instance, if you are doing something related with economy, you would like a kernel that takes into account something that is growing with certain cycles and those noise. By the way, I don't know if it might be useful for you. There's a kernel for that. There are lots of kernels for lots of applications. People have done a library. Still 10 minutes. So now we finish. So we are almost finished. Okay. Once we have this, we can substitute it by this. Molt bé, pues, vale, perdona. Gràcies per haver vingut. Now, k, x, y, if we define like this, we have the equation y. This is a dot product, isn't it? And we can express this kernel as a dot product. So now we would have which would be a vector times a matrix that would be K1, K1, 2, plus I, and Y. And here we can introduce this. And the notation for this vector, the notation would be minutes would be a star would be K star T. And this is that's it. And that's it. So now we can do lots of things. Introduce whatever distance we want. And there's still half an hour, which we will not do it. Perhaps we can do another day. We can meet. For instance, for solving Heise's problem, here we could use as a kernel Mahalanobis distance, which was what I have about half an hour of, and then you could take into account the fact that this is a spherical distance, but you would have an ellipsoid distance. So you can introduce your priors either like this in this equation, or by using the kernel and the Mahalanobis distance. And it was a very high, very strenuous escalation of the Everest, and only the heroes have survived all these 3 hours.
I am just a Sherpa.
Yeah, but look, they have survived. Perhaps another day we can, I could explain what is missing here. Hola, vaya, ¿te acuerdas que fui a buscar un café antes de venir aquí? Ya tenía cafés aquí. So, okay, so we'll leave it for another day, and another day we will finish the Mahalanobis distance.
So thank you very much.
Thank you for coming. And thank you for following.
Okay. So, any questions? Yes, regarding the similarity. In fact, when you write x transpose x, yeah.
And then there's the reserva que te unida.
So in some way you need a basis function here, right? You need a basis function.
Yes.
Thinking on the RAM matrix, so you are assuming that to have the RAM matrix that you say can be inverted, you should have a basis function. So a basis function, one way of thinking, it's a question, is can we think that a basis function to join these similar vectors? Because if they are very similar, let's say linearly independent, you lost the basis function. Yes. So somehow I wonder if there are, you could interpret this like as you have to invert that to be able to be inverted, you should have a certain level of similarity.
Of course, yes.
Just intuitively speaking, following.
Yes, that's true. That's true, because you are, of course, you could have like this and like this, no? Then it's, I am similar to all these and this, and the test one is similar to the, but these are almost parallel, so it would not exist. That's why you have this term here, this term here. With this term here, you are all these that are almost parallel, they are spread. And also, it might also happen here. It might happen that the vectors are different by doing the exponential, you make them parallel. So yeah, there's a bit of cooking.
So in this line, we call maybe what we can imagine or we can interpret intuitively speaking an orthogonal basis function like a very similar basis. Right? Because the relation is 0. So it seems to be a game between similarities and dissimilarities, right?
Yeah, okay. Yeah, nice. But the trick is, I am a test point, and you are the training points. So he has a certain relationship with you, you have a certain relationship with them, and so on. So probably, which is the way I am related with all of you is similar to the way that he's related with all of you. But you that are near me, probably your angles with the rest of ones are bigger than her angles with the rest of ones. So probably, if I have to use a value, I probably must use his value, her value, and your value. Because your angles are different than the angles that we have. Did you get it?
I'm sorry, I can't.
Yeah, this is AK, and these are the other points, and this is me. star. So let's imagine that he has an angle with the rest of you that is similar to my angle. And probably her angle is, with the rest of you, is better, more similar to both of our angles than your angles, with respect to all the others. So if I have to choose
distance.
yeah, an I, that similarities, because it's angle, it's not product, not distance.
It's like normalized.
Yeah, and the nice thing is that you could use this one, or for instance, if you want to take into account that you have scintillation, I don't know if here you have scintillation, instead of a 1 or 2, you could use 1. Because then, instead of being like this, it would be.
Okay.
So, and it's a similarity.
And let's say that closer distance means a smaller distance means high similarity, because it's that you showed
Yes,
before
yes,
the relationship between the distance and the scalar inner product. So this minus sign makes that both concepts are related with the contrary. One is high, the other is small.
But what they are using as the underlying operations are dot
Yes,
products.
it's more-
Anything that is a similarity can substitute it.
It's directly, you can think directly in inner product, so it's better to think directly in similarities. Good.
So I hope that you have enjoyed it and that it's useful. Anyway, if it's okay for you, I still have between half an hour or 40 minutes for explaining. You can introduce your prior knowledge into the problem from here or from here. So we have the prior knowledge here, but we could introduce it here, and that's what is missing.
We can discuss this in a meeting with maybe with Sasha,
Or which could
maybe
be free.
another seminar, maybe a small seminar. So thank you very much.
Thank you.
So in this way, if there are no more questions,
Then I have one.
please, Fabricio, go ahead.
The why? How you train this? How you train to obtain these values? Because for what I understand, you need the weight, of course, but you need the y too, the last one.
You mean, how do I train?
Yes.
You don't train, you use all the data.
You use all the data, and for the targets you estimate together with.
Yeah, the problem is that it's expensive because every time you have to do a forecast, you have to compute this and multiply this by the inverse. This inverse is computed once, but it can be expensive because if you have 1 million points, you have to invert a matrix of 1 million by 1 million. But what you have done it, you have it. So now you have a certain points, and every time a new point comes, you measure the similarity with all the others, and you discount the similarity between them. But you don't train.
Okay, the trains together.
Yeah, no, it's just using all the data. So it's a different paradigm. And another thing that is very interesting is that you can give the forecast and also plus less the sigma. Because you have the sigma. The sigma is phi star, there's one phi. And you have this because this is this. Is that exposed? Oh, yeah.
Yes.
Well,
Any other question? No? So thanks again, and looking
gracias por
forward.
invitarme. Thank you for inviting me.
Okay, so